like a webinar online, but for a number of different reasons, we weren't allowed to do that using email, and telesales was too expensive. So the thing I was doing was
All right. Hello, everybody. Welcome back to our data mining class on this lovely Monday night. Monday? Yes, this is Monday. So today we're going to go over frequent item set. And share my screen here. All right, so still remember what we have been talking about here. Mining frequent item set. Yes. All right, so we were looking, well, all right, mining frequent item set. We are looking at a really large data set, and this can be transaction data, right? So it could be Walmart transaction data. Where is my, it will be a large file, and each row would be a basket. In each basket, you have some items. We are looking at this market basket analysis. And we say you would have a few items in a basket, and together in your store, you will have many item types. And you also have many baskets, right? So this is your market basket model for mining frequent item set. And we said that we are looking for relationships between items. Consider all the baskets. And we are going to generate something called association rules, right? So this is something like milk implies diaper and so on. On each side of your association rule, every rule you have set. So this can be one or more items, or you won't have 0 items here. So to be, well, for association rules to be useful, we also want to generate a confidence score and also an interest, right? So confidence score, a confidence score tells you how confident you are about an association rule. Like when you see milk, how often do you see diaper? Interest tell you how interesting this rules is. If diaper is a very popular item, then this rule might not be that interesting, right? Because every item here would imply diaper, although they would have high confidence, but the interest would be low. Okay, so this is our association rules. Eventually, we want to generate them. But to be able to generate them, we will need to count frequent item sets. And frequent item set, let's start from a single item, say milk. And for each item set, when you, in this case, you have single item, you have something called a support. So the support for M is 60. So what does it mean, 60? Anybody? What does it mean, support of milk is 60?
It occurs in 60 baskets.
Great, yes, that means milk occurs in 60 baskets. So we also look at a support threshold. So very often in all these algorithms, you will see we will just say S. So support threshold just means if my support threshold is 60, that means everything equal to 60 or larger than 60, every item set that have support larger or equal to 60 will be frequent. Okay, so this is just one way to identify a frequent item set. Well, to define frequent item set given a large numbers of transactions. And we also talk about to be able to generate association rules, to be able to count them, we need to identify frequent item sets first. And we said that identify frequent singles, like milk, is easy because although you might have lots of single items, say you have 10 million of them, but to initiate counters to count them, each counter is 4 bytes, you only need 40 billion bytes of your memory, right? So you can fit this into your main memory, no problem. But if you want to count pairs, say milk and diaper, this becomes a problem because given the entire 10 million different types of items, this is the number of different pairs you would have, and this is usually much larger than your memory can handle. So you will need to have some algorithms to help you to efficiently calculate this without reading too many times, reading the entire file from the disk too many times. Okay. What else? We talk about to initiate the counters, we have this triangle method. We also have a triple method. For triangle, we are exploiting the index of a matrix, so we don't have to store the index. This way, each counter is 4 bytes, but the problem is we have to store a counter for every possible pair, even if the pair is not in your data set. For example, even if milk and diaper is not in your is not in any of your basket, if you want to use the triangle method to store your counters, you have to initiate a counter for milk and diaper. For triples, we only store the counters for any pairs that's in your basket, but the problem is you have to store milk, you have to store diaper, you have to store a counter, so it's 12 bytes. Okay. And that leads us to here, the a priori algorithm. So let's say even if you use the triangle or use the triple method, you still have too many items that you still have too many pairs that you have to count in your main memory. So what do you do? We are going to introduce a series of algorithms. They all based on a priori. So a priori is the first algorithm that we are going to look at. Okay, so if you're not talking, make sure you mute yourself. All right, for a priori algorithm, it's a two-pass algorithm. Remember what we meant by a pass. So in looking at all these different algorithms that can help us count frequent item set, we evaluate them by the number of passes they have to read the entire file from the hard drive, right? So this is 2 terabyte file. And we say an algorithm is pretty good if you require 2 complete pass of reading the entire file. Some other algorithms may need 4 passes, 5 passes to be able to finish. Then those algorithms will take more time because a pass of reading a disk takes a lot of time. So question, does this assume the file is not in memory? The file is never in your memory. It's only a part of the file that will be in your memory. So let's look at here. Your memory is 32 gigabyte, right? So you cannot feed the entire file in the memory. You have to read some file, process them in the memory, store some result, intermediate result here. Then you read the next one, you store the intermediate result, and you go on, right? So a good algorithm will be able to say, hey, if we read the entire file once, we will have the result. But I don't think there is such algorithm. For all these frequent item set algorithm, you usually need 2 passes. So the first pass, you read some, you count something, you read some, you count something. When you finish, you read from the beginning again, and you refine the result here to generate the final result. We will look at some of the algorithms. Okay, so are we clear? The entire file is never in the memory at the same time because the memory is just too small. All right, 2-pass algorithms. The key idea is this monotonicity. If you look at here, say if ABC is a frequent item set, that means, say, our support threshold is 60. And what does this tell you about the support of ABC if ABC is frequent? Anybody?
At least 60.
Right, so ABC support should be larger or equal to 60, right? Greater or equal to. In all this finding frequent item set, we also consider equal. So what does it tell you about BC, AC, and AB? About their support? Yes, they will be frequent as well, right? Because their support needs to be at least 60 for ABC to have 60, right? And what does it tell you about C? So everything here needs to have a support equal or larger than 60. So awesome. What does this tell us then? Well, if A only has a support of 30, would AB be frequent? Do you have to count? No, you don't have to count it, right? So then you don't have to count it. You don't have to count. Do you have to count AC? No. How about BC? Well, we don't know, right? Because I only tell you that A has a support of 30. I didn't tell you B and C. So this creates us a very nice way to eliminate the pairs or even larger size of item sets that we do not have to count. So in that case, we can save memory. Yes, it's like pruning your space of counting. So if you look at here, if a set of item I appears at least S times, then every subset of J of I would appear S times, right? So if this one has appeared 60 times, AB at least will appear 60 times. So if item I does not appear in S baskets, so if item I has a support smaller than S, then no pairs include I can appear in S basket, right? So if I has, well, if I has less than 60, I's support is less than 60, then none of the pairs that include I, let's say if I is A, we are talking about AB, AC, AD, none of them can have a support larger or equal to 60. All right, so based on this idea, how do a priori find the frequent pairs? Remember, we always talk about frequent pairs first, then we can generalize this to a larger item set. So in the first pass, a priori algorithm read all the baskets and count in main memory the occurrence of each item, right? So you're counting support of each single item. Single item. And this only requires memory proportional to the number of different item types you can have, right? So if you have 10 million item types, you will need 40 million byte memories, given that a counter is 4 bytes. So if an item that appear at least S times, these are frequent items, and we call this frequent single items. At the end of pass 1, you read the entire file. You check the count for each item. If the count is larger than S, we save it for the next pass. If not, we throw it away. So this tells you that pass 1 identifies frequent item sets of size 1. We are going to look at one example, so don't worry. Pass 1 finished, let's do pass 2. So in this case, we have not count any pairs yet, right? We only look at singles. In your pass 2, we are going to read the entire basket file again, and we want to count in your main memory only the pairs where both items were found to be frequent in pass 1. This requires memory not proportional to the square of frequent items only. For example, if we identify the number of frequent single items we identified is 20,000, the number of pairs that you have to count is C20,000 choose 2, right? So this is much, much less than your original number, C10 million choose 2. Then here we are going to require this memory to store counters and some memory to store the frequent items from the first pass. And the pairs of items appear at least S times will be your frequent pairs, right? After the end of pass 2, you look at the counter and you say if you have larger than S numbers, you are frequent pairs. So good. This tells you you require 2 passes to identify frequent pairs. And let's look at the memory and one example. All right. You have a large file, 200 terabyte. You have 32 gigabyte of your main memory. In your first pass, one pass is reading the entire file. You start to read the entire file, okay? So let's say the first basket is A, B, C. Second basket is A, B, D, and so on. And you have 10 million different types of items. So what do you need to do? Well, simple. You just allocate some memory space here to count this 10 million single items. Very often, you already know you have 10 million single items, right? Based on the ID, item ID. So say, all right, I have a counter for A. It doesn't really matter which data structure I use, but I think you can use, well, you should use a one-dimensional array because you're going to count every items, right? So let's say A is at location 0, B is location 1, C is location 2 in this array. So let's give you the array counter. This is the array, and this array has 10 median counters. Each one is an integer, so 4 bytes. In location 0, we are counting A, location 1, we are counting B, and so on. Okay. So after you read the first basket, what would be your array? What will be the value in your array? You have 1, 1, 1, and 0, 0, 0, 0, right? Are we good so far? Yes? No? Yes. All right. So what happened after you read the second basket? This one becomes 2, this one becomes 2, and still 1. D becomes 1, and 0, 0, 0, 0, right? What about this place? Do you use this memory space? Remember the counter is here. Well, this space is to help you read the files, right? So you can read it line by line. So first time you have ABC. Once you increment the counters, you can throw this away, free up your space, and read ABD, and so on. Okay, so great. After the first pass, what would be your result? Well, your result would be this counter array. What's the dimension of this counter array? Anybody?
Equal to number of items.
Number of different types of items, right? So it's 10 million. 10 million, not 1. All right. Now every counter will have a number, right? 60, 50, 40, 3, 4. And let's say your support threshold is 50. Would you be able to know which one is frequent? Yes, right. You just take this 50 and you say, all right, larger than 50, I will give you a true, true, false, true, and so on. Okay, are we good so far? So what's next? Remember what is our goal? We want to count pairs. To count pairs, we need to be able to do what? Oh, sorry, this one is false. To count pairs, we need to be able to generate counters. Well, the algorithm is very simple. The main point is look at how we consume memory. So we need to generate counters. How do we generate counters? Let's say you're writing a program, right? So you're writing a program. This is your current array. Let's say you don't use numbers anymore. Just to save memory space, you have true, false. You use bit array, super compact. What do you do next? We need to read the files again, right? So now you read the file, first basket, ABC. What do you do? Anybody? How do you do it? How do you count pairs?
A nested for loop.
For loops, great. Thank you. So for loop, what does for loop give you? For loop will give you A, B, and what? A, C, and B, C. So if you do a for loop and you see A, B, what do? You need to initiate a counter, right? How do you initiate a counter? What are the two approaches we talk about counters? You can use triangular matrix, or you can use triples, right? If you are going to use triples, it becomes what? In this space, because this frequent item sets, you're going to store your bit array. Here, you are going to store your counters. So to store your triples, you store A, B, and counter equal to 1. Awesome. So after this first AB, you have 12 byte. AC, you have 12 byte. ABC, you have 12 byte. Then you keep going on, right? So then you can remove this from your main memory. You read A, B, D, and for loop, and do this again. So great. Triples, very easy. How about triangles? How do you do triangles? Remember, the entire key of triangles is you need to be right. Okay, so great. People are saying that you have to initiate counters for all possible pairs. Awesome, that's very important. So what are all possible pairs here? That's from your frequent items, right? So think about this. If I just clear this, originally we are talking about A, B, C, D, E to 10 million. So if we are looking at this list, our triangle looks like this, right? The triangular matrix look like this. And what is the dimension of the triangular matrix here? You have 10 million here, and you have 10 million here, and you have to initiate all the counters. Are we good? So this location is what? The first location, AA, is at which position of the matrix? AA is 0, 0, right? Okay, 1, 2. Well, AA is 1, 1. If you start from 1, that'll be 1, 1. If you start from 0, it will be 0, 0. What would be this AB counter? What would be its location? Let's just say 2-dimensional array. Don't worry about the lexicographic order. For AB, it will be 0, right? If A is 0, then B is 1. So AB, it will be stored at 0, 1. AA is 0, 0. And we don't use AA, we use this one. How about AC? I know this might sound very simple, but just want to give you some idea. So AC will be 0, 2. Great. Now, are we going to, when we're using a triangle matrix, triangular matrix, in this case, are we going to have 10 million by 10 million? Well, we don't need 10 million by 10.
You use half, yeah, the triangle.
Right, we don't only use half. In the last case, in the last example, when we are talking about the triangular matrix. But in a priori, do we really need the entire triangle here? Well, because we already know that C and D are not frequent, do we have to keep some counter here for C and D? No, right? So some of them are not frequent. So we already know some of the columns, we don't have to count it, right? So for example, this column, C column, this will be all the different pairs that contain C. So we don't need it. This means we have to have some way to compact this triangle, right? Because you will have many empty space. So how do we compact them? Well, you have to look at these frequent items again. So let's say we have A, B, C, D, E, F, G, and A is frequent, B is frequent, C is not frequent, D is not frequent, frequent. Okay, so this is your indicator of frequent. And remember, originally, if we don't have this information and we want to create a triangle to triangular matrix to count them, your AB is at the location of 0, 1. Right? AB, AB, here. 0, 1. Great. So, but if we already know that these are not frequent, what do we need to do then? This is your original ID, 0, 1, 2, 3, 4, 5, 6, and so on. Well, yes, we have to skip them, eliminate them. Great. So both are correct. So to be able to do that, we will need to renumber all your item sets. So this is your original ID. Your new ID becomes 0, 0, 1. Then we skip them, 2, 3, 4, and so on. Okay, so you have to renumber all your single items, only number the one that are frequent. So eventually you will have 20,000 single items, and the size of the triangle, at least this dimension, will not be 10 million anymore. This dimension will be 20,000. Great. So then you have this triangle here. Let me use red color. You have the triangle here, and you can use the lexicographic order, and you count it. Okay, that's how you will be able to initiate a counter based on the renumbered item IDs. And then when you read A, B, C, you use 2 for a loop. You see A, B. Now what do? You know A, B is at 0, 1 because the new ID is still 0, 1. So you come in here to 0, 1, you just update it. Then you see A, C, you know it's not frequent. And if you say see A, E, where will be AE? What will be the new counter position of AE? We know that A is at 0, right? And E is at 2. Great. So you will need to use your new ID. And that is here. You have your item counter. Okay. And based on that, you know what items are frequent. You can use a bit array to store that information. And you have to map, you have to generate a mapping between the old item ID and new item ID so that you know what you are counting. And then you can use this space to count it. Okay, so this space, you can have triangular matrix if you want to use old item ID and the triangular matrix, or you just use triples. Okay, so we already covered this. You can use the triangular method, but if you want to use the triangular method, you have to renumber your item ID to be able to use them. All right, so what about, we talk about pairs, right? So what about, so there's a question, was the O item ID used in pass 1? Yeah, that's how you create a counter array, right? Remember, we have a counter. The easiest way to count for single items is you have this counter array, and the array size will be 10 million. Each component here will store a counter, and this first counter is for A at position 0. And this position 0 is the item ID of A. All right, so what about frequent items of other sizes? Because we already talked about pairs. So how do we do this? For each K, we need to construct 2 sets of K tuples, sets of size K. Well, K means if pair, we are talking about 2, triple, we are talking about 3. So pair is like this, right? M, D, triple is like M, D, and C. Milk, diaper, and Coke. And we know that the you will have a lot of this, but less number of this, because for triples to be frequent, it's really difficult. All right, so for CK, so let's look at some terminology here. CK is the candidate K tuples. These are the candidate because we think they might be frequent, but we don't know unless we count them. And LK is the set of truly K tuples after we count them. So if you look at the diagram below, you start from all items, every items, C. Then you count your single items, right? Like in the first pass of a priori using this count. array. Then you have your L1. This is what? L1 is truly frequent single items. Based on your L1, you know what could be frequent pairs, right? If your L1 it contains only A, B, C, what would be your C2? No, C2 is just candidate. Let's say you read all your item sets. Your A, B, C are the only frequent single items. What could be candidate pairs? What are the pairs that could be candidate? What are the pairs that could be frequent? All right, so someone has an answer A, B, and what? A, C, and B, C, right? Only the pairs that contain A, B, C. So that will be your C2. Then based on your C2, you have to count them. So in this case, you are using triangle because we pre-compute this. But if it's a triple, you don't have to pre-compute this. But you count all these possible pairs. Now you know what are the true frequent pairs, right? So eventually it turns out that AB is not frequent, but AC is frequent, BC is not frequent, okay? Then you take your L2, you can reconstruct larger size of candidates. In this case, you only have A and C. So you finish, you're done. There's no way you have a larger, there's no way you will have a frequent item set that has a size larger than 2, right? Because you cannot have A, B, C. You cannot have a, that's it. We are going to look at that later, but just look at one example. So our old friend, 8 transactions, frequent item set with support threshold equal to 3. These are your frequent single items, frequent pairs, and frequent triple. So let's look at how this works. You start by your C1, which are your candidate items, right? You have, this is all the different types of items you can have in your transactions. You count the support for item sets in C1, you count the number of B, number of C, number of J, and so on. Then you say, all right, only BCJM has a support larger or equal to 3. I think our support threshold is 3, right? So these are my frequent singles. So based on this frequent singles, I want to generate C2. Remember, what we can do here is to use a for loop, nested one. Then you have BC, BJ, and all that, right? Then you count every possible, well, every candidate in C2. Then you have your truly frequent pairs. Now you have to generate your C3. What would be your C3? Well, we have BCM. Okay, so BMC, great. BCM, BMC, BMM, BMB, BMJ. How come we don't have BMJ here? How come BMJ is not a frequent triple candidate? How do we know we don't have to count it? Could be an error in the slide. Okay, so someone has an answer, Asumi has an answer. MJ doesn't exist. Okay, great. Yes, because MJ is not frequent here, right? So if MJ is not frequent, for sure, this will not be frequent. So this is the only possible frequent triple, and we have to count it to be able to know if it is truly frequent. Okay, it turns out it's truly frequent. So great, this is your priori, and you know that now we covered from single to pairs to triples. And if you want to go on and find larger item sets, you just have to C3, generate L3, then generate C4 and L4, and keep going on. Okay. All right, so there is a question. How about CMJ and BCJ? So let's look at them. So CMJ, and what? BCJ. So for CMJ to be a frequent candidate, we need to have what? CM, CJ, and MJ as frequent pairs, right? But we do not have MJ. For BCJ to be a frequent triple candidate, we have to have what? BC, BJ, and CJ, and we don't have BJ. All right, thank you, everybody. Let's look at some
Professor,
summary. Yes,
could you go back one slide?
sure.
Yeah, for the third line, YL1 could only equal to BCJM. What about the other candidates like BCMN or BCMP?
Here, are you talking about this one?
Yes, yes.
This is a set. So this is not, you can have it in any order. This is frequent singles. This tells you that B is frequent, C is frequent, J is frequent, and M is frequent. It's not about BCJM in one set. It's counting the singles. I think you are confused about two large bracket with one bracket. This one is a frequent triple, has 3 items. This is frequent singles. Everyone has a size 1. Very good. Okay. All right. So for a priori algorithm, some summary, we have 1 pass for each K. This is the item size, right? So when you are counting frequent singles, you read it once, pass 1. When you want to read frequent pairs, you have some information from frequent singles, right? And you have to use this place to count frequent pairs. So pairs, pass 2. If you want to count triples, now you take all this information, you know the frequent singles, you know the frequent pairs, and you use this and read the file again to count for triples. Okay, so keep going. Oh. So this needs room in the main memory to count each candidate K triples. And this main memory we are actually talking about here and here, right? Unless you're the first passes here. For typical market basket data, some reasonable support K equal to 2 will require the most memory because you will have many pairs that you have to count. So support in all our examples, we are using a number like 63 and so on, but it's usually about percentage. So you will say if 10% of the basket contain this item set, then it's frequent. Okay, so it's a percentage of basket. And how do you decide on the support? I think we talked about this last time. You take a sample of your data. Say you have 1 million basket. You take 1,000 basket. So this will be 1,000 divided by 1 million. So it's 1 over 1,000. And then you use this to look at the data, try different support to see what would work for you, and then scale it up back to 1 million. Okay. In your assignment 2, you will be able to see the support has a high impact on the memory consumption of the algorithm. Because if you have a lower support, that means you have many frequent singles. Many frequent singles means you have to count many frequent pairs, and then you have to use more memory. All right, so that's your frequent item set, slice number 1. Let's take a 10 minutes break, come back, work on slide number 2. And let's come back at 6:55. If you have question, post it in the chat. I will answer them when I come back. All right, I am back. So let's look at the questions. First question, when talking about main memory, is it under the single machine context or multi? All right, that's a very good question. We always look at single machines because we want to be, although in the MapReduce environment or any clustering environment, you are looking at a cluster, but your algorithm, your map, and your reduce, they are running on single machines. So we need to have good algorithms to run on those single machines and utilize best utilize the main memory of those single machines. Let me give you one example. So when we are counting in a MapReduce environment, each of the map task is going to take, each of the map tasks is, can you see the screen? Oh, okay, it's on the top right corner. No worries. All right, so each of the map task is taking a piece of the file and counting something, right? And eventually we can put them together and say, these are all your frequent item set. But each machine is in charge of a piece of the file. And we're going to talk about an algorithm that will be able to help us to do this. But just pay attention here. Let's say your machine one is focusing on this part of the file. And the first pass, it's reading this. It's super easy because you don't really need that much main memory. Second pass, if we don't use a priori, what does it mean then? That means you will need to have a really large space for your triangular metrics or for your triples. And this might be much larger than your usable memory in this part. Okay, so the goal of using a priori is so that we can shrink. If you're using a triangle, we can shrink this triangle so that it will be able to fit in here. All right, so I think there are more questions. BMJ is not a candidate because BJ and MJ are not frequent pairs. But why can't we use BMJ directly? Because they are all frequent single items. Okay, so if you want to say, let's say, if BMJ appears 60 times in all the baskets, and 60 is your support threshold. What does this imply then? Let's say they appear together many times. Well, sorry, 60 times. We already know. That means you have at least 60 baskets. And that also tells you that BM, MJ, and BJ will have at least how many occurrences? 60, right? So if any of the pairs that you can derive from this triple does not appear 60 times, that means the triple will not be frequent. Next question. Why does k equal to 2 require most of the memory if you have to count into main memory all of the frequent pairs during pass 2 for any k greater? I don't really get the question, but k equal to 2 require most of the memory because your filter, you only have one filter. If you think about all these filters, help you eliminate the item sets that you don't have to count. The first part, you only have one filter, help you to eliminate the singles So you still have, in our example, TDC 2000, choose 2, right? And once you have this L2, now you have more filters. Like the answer for the previous question, if you look at BCM, we know that BMJ cannot be a candidate because BJ is not frequent, right? So more filter help you remove more things that you don't have to count. Your triangles or your triples will require less memory. And also the chances that longer items become a frequent item set, it's smaller than the chances of a pair or a single item to be frequent. So one more question. Since the memory requirements are focused on storing the counts, is it assumed that we read from the file line by line, basket by basket? Yes, you read it line by line. You only read the things that you need. You never read more. All right, so this is a priori, very easy. And okay, so how does, so one more question. How exactly does L2 construct C3? Well, you take this and you generate all possible triples, right? You take B, M, and then you look at the next pair. You say, all right, I already have B. I don't have C. Let's put BMC. Do I need BM2? Can I have BMC? MC, I do have MC here, so good. Then you take BM, you look at this one because you already finished this one, then BMJ. You basically just use for loops, for loops to scan them. You might have other ways to do it, like you put it in a really fancy queue or hash table to do it fast. But remember, our key is not to do that part fast because this is tiny. The time to compute this in main memory is really minimal comparing to reading files from the disk. So the only thing that we want to evaluate the algorithm is how many times you have to read the entire file from the hard drive, okay? All right, so now we understand a priori. We are going to look at different ways that we can improve a priori. So the same idea, but we are going to talk about, I think today we might have time to cover 3 algorithms, and we're going to talk about other algorithms on Wednesday. The first algorithm is the PCY algorithm. So PCY algorithm, oh, you guys don't have the slides, right? Let me upload the slides real quick. All right, you should be able to find the slides on Piazza. Okay, so PCY algorithm. So how do we improve a priori? Well, before we talk about improvement, what does it mean by improving a priori? Anybody? This is a priori. Pass 1. We only discuss the cases that you're counting pairs. Pass 1, you use this memory. Pass 2, you use this memory, and you use here to count. In what case a priori will fail? being a two-pass algorithm. In what case, a priori will need a third pass to count pairs. Anybody? No one? When the number of distinct items does not fit into main memory, too many pairs to store in main memory. Great, thank you guys, thank you. So the cases that, well, one of the case that a priori will need an additional pass is this part is not enough to store your triples or your triangular matrix, right? In that case, you have to store the intermediate counter into the file, read the file again, and all that. It's totally a mess. So, for example, let's say for a given basket file, 200 terabyte, and your priori require 2 passes to count pairs. The improvement we are going to make is to make your priori still require 2 passes to count pairs, but we'll be able to handle maybe 400 terabyte, okay? Twice number, if you're not talking, please mute. So the improvement is we want to be able to handle a large file. Is that thrashing? I have no idea what thrashing is about. So our goal is to be able to read a larger file and still in 2 passes. So let's look at how this works. Okay, before we look at how it works. So hey guys, can you mute? Let me find the person who's talking.
这是我的Clubhouse 的高光时刻。当然我并不想知道那些 A 片是谁放的。然后我还想分享一下我对。
Mute. Yes. Yeah, for me to mute, I have to find the person and click on mute and all that. But I did it. Where was I? Oh, improvement. So our improvement here is we want to be able to process a larger file. Okay, so that given this pass 1 filter here, we want to feed the counter into here. So what stay the same is your memory space. We have 32 gigabyte, 32 gigabyte. So how do we improve this? Well, the outcome of the improvement should be less candidates that we need to count. Right, a small triangular matrix or a small number of triples. That means we have to have a more powerful filter from here to here. And currently our filter is only single items. How do we construct a more powerful filter? Well, the observation here for the PCY algorithm is, hey, during your first pass, you have a bunch of memory space that you have never used. Can we use them to create a filter so that we can use those filter results in your second pass to make the triangle even more compact or have less triples to count? So how do we do this? In the PCY algorithm, the observation is pass 1, most of the memory is idle, right? You only store the individual item counts. Can we use the idle memory to help us create a filter so that we will be able to reduce the items we have to count in pass 2? So pass 1 of the PCA algorithm here, in addition to count the occurrence of single items, here we also want to maintain a hash table with as many buckets as possible in the memory. Remember your first pass looks like this. You have some memory space here. So you based on this memory space, you say, let me create some hash table. Hash table looks like this. Key, value, okay? So assuming that a value is 4 byte, a key is 4 and 4 byte. So an entry in your hash table is 12 byte. And let's say this memory space is 24 byte. I'm just making this up. You can have 2 buckets, right? Very simple. But in practice, you have more memory space. If you have 24K bytes, then you can have 2,000 buckets in hash table. All right, so you create a hash table and you keep a count for each bucket. And that count for each bucket will help you to record the pairs of items that got hashed into the buckets. Okay, so it's about the pairs of items, not the items. Sorry, it's about all the pairs that hash into the buckets, not single pairs. Let's look at some examples. All right, algorithm is here, but since we don't have much time, we can come back to this later, but let me use a whiteboard. Let me use the whiteboard and tell you the basic idea of PCA, and we can come back to the slides next time. Because we are going to have a quiz on 720. Okay, PCY, very cool algorithm. Pass 1, pass 2. Remember in a priori, this is counting single items. This is your frequent single items. And you might have some mapping to create a new index. And then this stores your triangular matrix. Okay, so what do we do for PCY? Well, in PCY, we're going to create a hash table here. Hash table will have key, value, pairs. What would be your ultimate hash table that you want? The ultimate hash table is your key will be individual pairs, right? So let's say your item is A, B, C for the first basket. Then your first entry, well, one of the entry in your hash table would have A, B, the other one will have A, C, then you have B, C, and so on. So this key will, the key will capture all possible pairs, right? So that will be 10, C, 10 million, choose 2. And the value will be counting how many occurrence of AB that you've seen so far, or AC you've seen so far, based on your first pass of the entire file. Are we good? Is this possible? So there's a question. This is happening before you know which single pairs are frequent. Yes, this is before we know which single pair are frequent. Just look at this. We read ABC, right? And we start to increment counter for A, counter for B, counter for C here. But at the same time, we look at this hash table. We say, all right, key equal to AB. Let's make the counter 1 because this is the first time we see it. Is this possible? Okay, great. I see some great answers. Okay, so yeah, we cannot store the entire hash table because if we can, we don't really have this problem of big data, right? You have many, many different pairs that you have to count, and this hash table is too big to fit into your main memory. And Christina is correct. This is inefficient because some of them will have a count 0. We don't have any filter yet, so we don't really know which one will be 0. So what would be a way to efficiently use this, since we're not using it anyway, but make more sense? So instead of having AB, AC, and all that, having a counter, we just do a very simple hash table. Say I only have space for 2 buckets, okay? I don't have memory space for each pair. My first space stores, I have a hash function. This hash function says, take your possible pair, because from here we have possible pair A, B, B, C, and A, C, right? And renumber them. So this one will be 0, 1, 1, 2, and 1, and 3. Okay, great. And we put smaller number here, larger number here. And we say if this is your I, this is your J, if I equal to, if I is an odd number, go to bucket 0. Bucket 0, else go to bucket 1. Okay, so based on this, you say, all right, 0, 1, I is an odd number. Is 0 an odd number? Shouldn't AC be 0, 2? Yes, sorry. Is 0 an odd number? No. So 0, 1 will go where? Bucket 1. So you will just increment 1. 1, 2 is I an odd number? Your I is 1, right? Is 1 an odd number? Yes. Then you go to here. 1, 2. Is 1 an odd number? Yes. And then you go to here. Okay. So you do this for every possible pair when you are reading your all the baskets in pass 1. And eventually, without going into the details, this becomes very interesting. So let's say your support is 60, and now you have this value is 60,000 for the first basket. You have many, many pairs that I is an odd number, so it goes to here. But this basket, you actually have 50. Number is 50 after the pass 1. What does it tell you then? Well, this tells you every pair, if I is an odd number, we don't really know if it is frequent, right? Because together, they're very strong. They have 60,000 hashes. But if your I is an even number, can you be frequent? You cannot really be frequent, right? Because even if one pair got hashed into this bucket 50 times, you are still lower than 60. So the only thing that we can tell from this result is, all right, anything that hashed to here is not frequent. Great, we have one more filter, but anything that hash into here can still be frequent, so we still have to count it. Okay, so this is the basic idea of PCN, and we are going to continue on this next time. All right, so questions. Does that mean we would count each pair 2 times, 1 in first pass? Yes, 2 times. If it is even, we know it's not frequent. Yes, only when the number is lower than support, then we can have a good filter. All right, so your quiz is on the Blackboard. Make sure you download it, and you need to turn on your camera for your quiz. If you don't turn on your camera, you have, right now we say 10% penalty, but I think we're going to make it larger. So make sure you turn on your camera. So question, if they are both larger than 60, then you don't have any filter. Right. In that case, you don't have any advantage. Is our TA here?
Yeah, I'm here.
Okay, great. So your TA is here. If you have any questions, feel free to ask. Make sure you submit your quiz on time. And when we say short answers or ask you to describe something in the quiz, it's usually a few sentences is fine.
All right, guys, time's up. So please remember to upload it to Blackboard. My peer? Here? Are you still working on it?
I'm submitting now.
Okay.
Thanks. Just download this one.
Are you done?
Yeah, I'm submitting now. Okay, thanks.